Hello, welcome to General Chemistry 2. I chose Thermochemistry to be the first unit to discuss, and it deals with heat transfer. So on this cover page, I show two reactions. One is used in hand warmers, something that I used as an undergrad in the winter walking between the dorm and the lab at NYU. Here in red is what happens with cold packs, something much appreciated after maybe a jog around campus around UT Austin, where I did my graduate work. But more stories about school later, more information about this equation in later videos as well. Because for now, I want to go over some key definitions. Now, the full title of this unit is Thermochemistry, Energy, Heat, Enthalpy, and Calorimetry. I want to look first at the definition of thermochemistry and some key terminology. Thermochemistry is the study of the relationships between energy and reactions, chemical reactions, and processes. Now, this is a subset of thermodynamics. You remember your first and second law of thermo? We'll talk about that in a later video. Subset of thermodynamics. Next, I want to differentiate between system and surroundings. It's going to be very important that you differentiate between systems and surroundings because your professor may ask for the energy change of the air around a reaction, and you have to decide, is your professor really asking about the system or the surroundings? And for example, let me put here a cube or a chunk of CO2, dry ice. CO2 solid. And you know that the solid will sublime. It will change into a gas, bypassing the liquid state. So this chunk of dry ice is going to be sitting on a table. Okay. And the system is the part of the universe that you want to study. And the surroundings are the rest of the universe. Now, it's totally valid that your professor will ask about the desk, absorbing heat, releasing heat, and in that part, or that case, the desk is the system. But for this, I think it's pretty obvious, or makes more sense that the dry ice is the system, and what's the surroundings? The desk, the air molecules. Is that it? I think that's about it. And the system itself is the CO2 going from solid to gas. I would call this a chemical, or I would call this a process rather than a chemical reaction. It's just a change in the phase. The next diagram that we want to be comfortable with is an energy diagram where the energy is this y-axis. Okay. Sometimes that axis is going to be energy. Sometimes it's going to be heat. Now these terms are interchangeable, and that's okay for most cases, but there is a difference between heat and energy. And before we fill in the middle part of this diagram, let me give you now the definition for heat. So heat is literally the transfer of thermal energy. The movement of thermal energy is heat. So an object can have thermal energy. You really only describe or talk about the heat when there's a transfer or movement of that energy. Now on this diagram, I want to put the reaction for the hand warmer, and I'm going to put the reactants up here. 4Fe solid plus 3O2 gas. So by the way, how do you make this? You get iron and you evacuate it. And then when you open up the package and it reacts with oxygen, it starts to release heat. So the release of heat means you're giving off energy. And this is where I would put the reactants. And then when it gives off energy, you form these products. 2Fe, 2Fe2O3 solid. Almost forgot how to balance. Okay. Heat is released. That's why this is lower. You could almost think of it as a ski slope, where you have a lot of potential energy at the top, and in this case, if we're looking at a ski slope, the skier is releasing it as kinetic energy. Okay. Now, you might be familiar with this term. If a reaction gives off heat, that is called exothermic. And if it absorbs heat, you know that is called endothermic, or you might be familiar with those two terms. For the cold pack, that reaction absorbs heat. That reaction is endothermic, and I would have the starting material at the bottom and the products at the top. Okay, it will go in the opposite direction. Heat is being absorbed. Okay, next. I am throwing out a lot of terms that are very similar. Heat, energy. I talked about potential versus kinetic energy. Let me give you a very, for me, useful chart which shows the manifestations of energy. Different forms of energy. Okay. At the very top, we have energy. And energy for us is going to be defined as the capacity to do work, or it has the capacity to do work. And we'll talk more about this term work in a later video. We have two main types. This one is going to be kinetic, the one on the left, and that is energy due to motion. Oops. And on the right, we're going to have potential energy. It's due to, let's say, location or position or composition. For instance, the skier has a lot of potential energy due to its location. These chemicals have a lot of potential energy because of their composition, and when they mix, they release heat. Next, what's related to kinetic energy is thermal energy. Right? The motion of particles or atoms manifests itself as kinetic energy, and when any heat that's produced is transferred, that is thermal energy. And it's associated with temperature. Potential energy is chemical energy for most of the cases that we'll be looking at. And that is associated with positions of electrons. So we're still looking at location and positions of electrons and nuclei. We could take out chemical energy as these atoms react with each other. Okay. All right, so that is a pretty good chart that tries to incorporate a lot of terms that I've been throwing around in this first video. Next. Let us delve a little bit deeper into energy, and let me give you the definition for internal energy. I'm still trying to figure out how to color code my notes. It looks like these light blue is going to be definitions defined in black, and then anything that's really important I'll set off with green or pink, it seems. But internal energy, that is U, the symbol U. And if we think about the internal energy of a system, that is the sum of kinetic and potential energies. And in chemistry, we're going to be concerned about those two energies of all the particles in a system. We're going to be working with U in the next couple of videos. Now, what is the unit of energy? Okay, let me give you an equation, and I do this typically. Most of my equations are going to be set off in green, and the first equation that we're going to see in General Chemistry 2 is kinetic energy equals 1/2 mv squared. We won't be using this a lot, but I want to use this as an example of how to do unit analysis. Because kinetic energy is energy, and it has to have an associated unit, and we're going to try to figure that out. So mass is in kilograms. Okay. Sometimes it's in grams in other equations, but in this equation it's in kilograms. Velocity is meters per second, and we are squaring only the velocity, not the mass. How good is your unit analysis? If given these units for these variables, what is the unit for kinetic energy? Go ahead and give that a shot. You could pause the video if you need to. The unit for kinetic energy is, well, simply kilogram meter squared over second squared, because it's coming from the squaring of velocity. But we're not going to use this specifically as a unit because there is a conversion, and the conversion is, what color do I want to use? I'll use pink. 1 kilogram And you can put a dot if you want for multiplication. I want to get this as neat as possible. Seconds squared equals 1 is called a joule. And the abbreviation for a joule is just a capital J. That is the energy unit, 1 joule, which is equals to 1 kilogram times meter squared over second squared. Now, we know other units of heat and units of energy. You might be familiar with the calorie. 1 calorie, and the abbreviation is CAL, equals 4.184 joules. Now, the peculiar thing is that when you think of a calorie in terms of food, a food calorie is actually different. A food calorie is actually 1 big cal with a big C, and that's equal to 1 kilo cal, little c. So if your piece of bread is 80 calories, it's really 80 kilocalories, and then you can convert that into joules in terms of the energy potential from that piece of bread. I have one last topic to go over in this particular video, and that is what a state function is. State. What's going on with my spelling? State function. It's a property that is determined by the state of the system. Not how the system arrived at that state. So not how it arrived at that state. Kind of a weird definition. Let me give you an example, something that you might more easily relate to. Let's say we have a hill, or maybe not even a hill, a mountain, and that mountain has an elevation of maybe 5,000 feet. And we have two people. We're going to start those two people at the bottom. One pink and one purple. And the pink person will trek as a direct path to the top. And let's say that person, it took them 3 miles of walking. Okay. The other person wants to stroll, maybe not exert so much energy going up, so they'll take more of a flattened path. Okay, less steep, maybe is what we can say. Okay. And that person walked this path for 15 miles. The elevation is a state function because both of their delta elevation or their altitude is the same. So altitude, or you could even think of it as elevation, is a state function. And we could think of it as a delta, for instance, delta altitude. They have the same delta altitude. The starting point and the final point. Oh, by the way, when you have a delta, think of it as altitude final, 5,000, minus altitude initial. So think of final minus initial. Initial is 0. So the delta altitude is 5,000 feet. And it's the same for both people. But the path, or not even the path, the distance walked, is what's called a path function. So that's the opposite of a state function. And in this case, it's the distance walked. They're different, 3 miles versus 15. So what are some chemistry properties that are state functions, and what are some that are path functions? State and path. I can tell you now we're going to be mostly concerned with state functions, and some of those examples are let's see, temperature, volume, pressure, and then the associated change with those state functions you know as delta T, delta V, and delta P. But now we also have energy, and I'll use internal energy U. Later videos will talk about change in internal energy. But what about path functions? Where it's dependent on the path. It will change depending on how that system got from the initial state to the final state. So path function, let's see, could be work, and technically heat. Heat is a path function, but temperature is not. Okay? And we'll delve more into that in the next video when we talk about W and Q. Alright, so I'll see you in the next video.